we are moving in the direction of stochastic analysis. Okay, basically we said that the flow or the headway, they don't have a definite value in the traffic, okay, because they are not uniformly distributed. So when you say there's a flow of 3,600 vehicles in an hour, it doesn't mean every vehicle after every second. Okay, so the headway can be unevenly distributed. So any headway 2-3 seconds has a chance of being there. And we looked at the equations from which you can calculate the probabilities. And using those equations, you can also calculate the chance that the vehicle can enter into the flow in the gap analysis. Now we will move on to the queuing theory. Okay, so we already did something from it when the shock waves. Okay, so we did some sort of queuing theory analysis with the shock waves. But here we will be talking about basically the congestion. Okay, so the shock wave can even be because of the signal as well. But with the queuing theory, now we are focusing more on the congestion. Okay, so congestion results, as we know, in the form of queues, and it can be on expressways, it can be on ramps, off ramps. Okay, different types of intersections. Okay, so this theory basically has the algorithms or the equations which describe the process resulting in the formation of queuing. Okay, so how the queues are formed, equations explaining how the queues are formed, that is queuing theory. Okay, and we discussed earlier, we started this chapter with traffic flow theory. So I defined that the theory or the equations which define traffic flow. Okay, so the same goes with queuing theory as well, the equations or algorithms that define queuing. Okay, when we are considering the queues, there are certain factors we need to take into account. Okay, first of all, the arrival patterns. So we have already discussed them. Arrival patterns basically relate to the flow, the type of flow you have. So you can assume the flow to be uniform, or you can assume the flow to be probabilistic. Okay, Poisson distribution. We already did the equation with Poisson distribution. So these are the most commonly used flow assumptions. Okay, so arrival rate refers to how the flow is coming. Is it is it uniform or is it probabilistic? Deterministic or probabilistic? Uniform Poisson distribution. Then how many channels you have? Okay, now channels is how many from how many lines you can serve the flow. Okay, how many lines you can serve the flow. Okay, so if you are talking about a highway, an intersection, so number of lines, the number of lanes you have on the highway. Okay, so if you have 3 lanes, there are 3 channels. The cars can move from 3 different lines. Okay, if I am talking about a highway, same thing goes there. On an intersection, the channels will be different for each movement. So you may have a channel for right turning, channel for left turning. Okay, so you have to look at the specific channels, then the specific lanes, and later on you will see that in some cases these channels are referring to service booths. Service booths. Okay, so service booths basically means let's say if you are going towards Causeway, let's say, so you have to they are counters, right? They are booths there. Some booths you have to pay something, okay, or you have to do the immigration, the passport check, and so on. So how many of them are there in parallel? Okay, we are talking about parallel booths here. Okay, or they can be series as well. So number of channels either means from how many lines the vehicles this flow can be served. Okay, for a highway, these are just lanes. For an intersection, these are lanes in one direction. or one movement, and for these checkpoints it would be the number of booths you have. Okay, so same thing happens at the airport, same thing happens in the banks. Okay, how many tellers are open? So these are number of channels basically. Then you have the queue discipline. Okay, how the queue is served. So there's a queue. Okay, we are talking about queuing theory. So there's already a queue. This is a given assumption. Oh, the queue is already there. So we have two approaches to serve the queue. Okay, one is called LIFO, the other one is called as FIFO. Okay, last in first out, first in first out. Okay, last in first out means the vehicle or the person who is last in the queue will be served first, and first in first out means the person who is first in the queue will be served first. Okay, last in means you are the last person in the queue and you will be the first to leave the queue, and first in first out means you are the first person in the queue and you will be the first one to leave the queue. Okay, now my question is, which one of them applies to traffic, LIFO or FIFO? Which one for traffic queues?
First in, first out.
First in first out. Yeah, it should be, right? Should be, huh? Yes, first in first out. This is what we assume, right? That the queue will leave from the front. Okay, and yes, but we have some, very skilled drivers. They find their way. They come from other lane and shoulders and whatnot. Okay, so now we will move on to different queuing scenarios. Okay, we will move on to different queuing scenarios, starting with deterministic scenarios, deterministic analysis. Okay, so the flow is coming in a deterministic way. It's uniform. Okay, the flow is uniform. It's coming in a uniform way. Okay, now you see here they have different terminologies here. Okay, D1. Okay, the first D refers to arrival. Okay, the second D refers to departure. Okay, type of departure. First D type of arrival, second D type of departure, and one means number of channels. Okay, number of channels. So DD1 means I have deterministic arrival, deterministic departure, and I have one channel. Okay, deterministic arrival, the flow is coming uniformly, so there is a fixed interval between every two vehicles, no probability. Then deterministic departure as well. Okay, so between every two vehicles which are leaving the lane or leaving the booth, there is again fixed interval. And how many lanes or how many channels I have? One. Okay, now within this scenario DD1, I can have four cases. Okay, within this context I have four cases. These four cases are that so arrival is referred to as demand, arrival is referred to as demand, and departure is referred to as service. Okay, so demand and service. Okay, so the first case is that vehicles are they have a constant demand condition but varying service rate. Now here at this point, before I move on to these cases, I want to explain the difference between variation and probabilistic. Okay, so for example, the flow in 1 hour is 3000 or 2000, let's say. Okay, flow in hour 1 is 2000. Okay, in hour 2 it becomes 1000. So it's varying, right? It's varying. But in the first hour, when it was 2000, the interval between each two vehicles was the same. So 2000 was equally distributed. Okay, in the second hour, the same phenomena, the same thing, that it is equally distributed, but now for only 1000 vehicles. So earlier it was equally distributed between 2000 vehicles, but now it is equally distributed between 1000 vehicles. So the flow is changing, but the type is not changing. Okay, so we will call it varying demand. Where is it? Varying demand. Demand is varying, but it is still deterministic. Okay, it is still deterministic. Okay, but if I say demand has a chance of being 2000 and being 1500 and being 1600, this is where it will change the type. Okay, this is where it will change the type when I talk in terms of probability. Okay, so even within deterministic type, the demand or the service rate can change. Okay, but whenever it changes, the interval between them is constant. Okay, I'm still talking about a fixed value. So I'm saying first 10 minutes 500 vehicles, one value. Okay, there's no other value. Next 10 minutes 200 values, one value. Okay, so deterministic means when you are just giving me one value for every time interval. Okay, but variation means that from one time interval to another time interval it is changing. It is changing. It's still one value, but it is changing. Okay, so now you can see I can give you I can tell you that during different time intervals the demand is constant. Okay, but the service rate is changing according to time. Okay, according to time, not chance, not probability. For every time there is a single value. Okay, so this will be the first case. The second case will be varying demand. So the people who are coming, they are changing according to time. Their number is changing according to time, but for every time single number. But the service rate is constant. Service rate doesn't change. The way they are being served, the way they are leaving, it is constant with respect to time. Okay, the second one is both of them are constant for every time interval, no change in value for demand or for service. And the last one is both of them are changing. So from one time interval to another time interval, I have different value for demand and different value for service. Okay, so these are the four cases. Okay, so all of them are deterministic, no probability here. Okay, and all of them have one channel only. Okay, so any questions up till this point? It's all clear?
Yes, doctor.
Okay, thank you. So moving on, we will be like now you understand the scenario, so you will dive straight into the examples. Okay, so for each case there will be an example. So we have now constant demand and constant service. Okay, so according to time it doesn't change. Okay, so vehicles are entering at a recreational park. Okay, and there is a single gate, and on this single gate all vehicles have to stop. The park attendant will give them a brochure. The park opens at 8 a.m. Okay, at which time the vehicles begin to arrive at a rate of 480 vehicles per hour. Okay, so this is the demand rate. Okay, at 8 a.m. Then 8 to 8:20, the demand the demand arrival declines to 120 vehicles per hour. Okay, so from 8 to 8:20, 480 vehicles per hour. Then from 8:20 onwards, 120 vehicles per hour. Okay, and it continues at that level for a remainder of the day. Now you may say that it is changing according to time. Why you are saying that it is constant demand and constant service? If you look, when we will look at the second example, you will get some clarification. What do we mean by changing according to time? Okay, this is like in one time interval, the whole time interval only one value. This is almost a constant number. Okay, so when we say varying according to time, it means as a function of time. So for every second there can be a different value according to time. Okay, so we are not talking about this variation. We are talking about variation which happens very rapidly. Okay, very rapidly, like every minute and every second, something like this. Okay, but for a whole set of time, if it is a single value, okay, and then it changes after some minutes and some second for once. It's almost negligible. Okay, so we can still consider it constant. Okay, so as we said, for these vehicles, whatever the rate of arrival is, the service rate is the same, which is 15 seconds for every vehicle. So every vehicle has to stop for 15 seconds, and the 15 seconds, the guy at the booth is giving them the brochure, okay, and he's telling them, okay, you have to go there and where and so on and so forth. Okay, so must be a very big park where people go in and they can get lost and so on and so forth. Okay, the same thing happens when you go to city center, like it happens to me. I don't know about you guys, but it happens to me. Like I go in city center, I don't know where to go. Okay, so when there's a big park, like you need something, right? So they have the maps and the counters there. Anyways, so these guys have this guy there who will give them the brochure and giving stopping the vehicle, giving the brochure, then moving it requires 15 seconds. So the service rate is 15 seconds. It's not even changing between different time intervals as well. Okay, you have to calculate the arrival rate per minute when the time is, so the time starts at 8 o'clock when the park starts. Okay, the time starts at 8 o'clock when the park starts. Okay, uh, so arrival rate when time is less than or equal to 20, it is given. Okay, what is the arrival rate per minute when like we just have to do some conversion, but from where will I get the arrival rate per minute for less than equal to 20? Which one is it? Yeah, tell me. The arrival rate per minute when the time is less than or equal to 20. So starting from 8 o'clock till when it is less than equal to 20. What is the arrival rate? Where it is given? What value is given? Yeah, tell me.
480.
Yes, 480. So this is 480 per hour. Okay, 480 per hour. So you have to convert it to per minute. Okay. So how much is that?
8.
8 per minute. Okay. Then for when the time is more than 20, okay, then it is 120 per hour. Okay, so 120 per hour, so 2 per minute, right? Okay, so this is done.
Yes.
Departure rate per minute. Now for departure service, 15 seconds. Every vehicle takes 15 seconds. Okay, so if every vehicle takes 15 seconds, then how many vehicles can I serve in 60 seconds? 1 minute is 60 seconds, right? 1 minute means 60 seconds. So every vehicle takes 15 seconds, and 1 minute I have 60 seconds. So in 1 minute I can serve 60 upon 15. The total time I have 60 seconds divided by time per vehicle, which is 15 seconds. So in 1 minute I can serve 4 vehicles per minute. Okay, is it clear up to now?
Yes, doctor.
Okay. Total number of vehicles arrived during time t when time is less than uh, 20, when time is less than equal to 20, and then when time is more than 20. Okay, so we are looking for equations here, because they did not say okay time 2 minutes or time 3 minutes. So they are looking for equations to calculate number of vehicles arrived. Now when time is less than or equal to 20, vehicles are arriving at 8 per minute. 8 per minute. Okay, so if I want number of vehicles, it will be 8 into time. Okay, and if I need for time more than 20, then what should I do? For time more than 20, what should I do? It was 2 per minute, right? 2 per minute. So what should I do? N equals to what? Yes, when time is more than 20, what will be the equation for number of vehicles? Yeah, anyone? If for less than equal to 20, it was 8 into t. So 8 per minute multiplied by number of minutes. For time more than 20, what it should be? It was 2 per minute, right? So what should I write here?
Eight multiplied 20.
8 multiplied by 20, why? The vehicles are arriving at 2 per minute. So it should be 2 into 20, right? 2 into okay, 8 multiplied by 20, yes, 8 multiplied by 20, okay, that's good, okay. Then 8 multiplied by 20 plus
2.
2t. Okay, so what's the logic behind it? When you say time more than 20, okay, so the number of vehicles which were supposed to arrive in the first 20 minutes have already arrived. So we are talking about vehicles after them. So the first 20 minutes I will add by default. So that's where 8 into 20 is added. Okay, and then 2 into t, which is the rate multiplied by the time. Okay, so that's why we did that. So 8 into 20, you don't have to write 8 into 20, you can just simply write, I believe it will be 160. Okay, so I can write 160 plus 2t. Okay, so this can be written like this. Okay, understood? Okay, the next thing is number of vehicles departed during time t. Okay, so this is very easy. The departure rate is the same first 20 minutes or the last 20 minutes, which is 4 per minute. Okay, so n equals to 4t. There's no change here. Okay, and then we have to plot the arrivals and departures versus time t. Okay, so use these equations to plot the arrival and departure. Okay, I believe it should be, yeah, okay, so it's there. Okay, so arrival and departure. Okay, so up till here we were using the first equation, which was 8 into t. From here onwards it is 160 plus 2t, that equation. Okay, so in those equations you will put different times t equal to 0, 2, 3, 4, 5, whatever, up to 1 hour, up to 2 hours, whatever number of hours. Okay, it doesn't matter. Okay, so now you can see here at this point, when time was vehicles were arriving at 8 per minute and they are leaving at 4 per minute. Okay, so there's a queue there. Okay, you can see the queue over here. Why is this is a queue? Because the service rate is low, the arrival rate is higher. This is 8 per minute and this is 4 per minute. So you have the queue here. Then at this point, when the time is 20 minutes, okay, the arrival rate dips to only 120 per hour. 120 per hour, yes. So it dips to 2 per minute. Okay, service rate is 4 per minute. So it will start to eat the queue. So there are only two vehicles coming every two new vehicles coming every minute, and the booth is serving 4 vehicles in a minute. So it's taking 2 extra from the queue. Every minute it is taking 2 extra from the queue. Okay, so this is it. So and this is the time when the departure and arrival both intercept. Okay, so departure arrival both intercept means the queue clearance. Okay, the queue clearance, and this happens at time 60. You can see here. Okay, at time 60. Okay, so any vehicle which comes from 8 o'clock till 9 o'clock, 60 minutes means 9 o'clock, right? 1 hour. So any vehicle which comes between 8 and 9, they will see the queue, they will join the queue. Okay, any vehicle which comes after that, they will not have any queue, so they'll just come at the booth directly, spend 15 seconds for the brochure and then leave. Okay, so the time in this first hour when the queue is there, how much is the delay? How much is the delay? So in this graph, for example, I want to know the length of the queue at time 10 minutes. So I can go to the graph. How many vehicles served? This many. How many vehicles arrived? This many. So their difference is the length of the queue. Okay, so the graph can give you length of the queue at each time instant, at any time instant. Okay, at 0 it is 0, then at 60 it becomes 0, and between them it has a value which you can get from the graph. Okay, so the graph can give you time, queue at any time instant. It can also give you the delay as well. Okay, so for example, this is the 100th vehicle which has come to this booth. Okay, so it came at this time and it left at this time. Okay, so this is the delay for the 100th vehicle. Okay, you can also get the delay for this 160th vehicle. Okay, so for any vehicle which is in the queue, 160th, 240th, 200th vehicle, whatever vehicle. Okay, when you take the difference between the two times, arrival and departure, you will get the delay. Okay, so this graph can give you the queue length at any time instant. It can also give you the delay for the driver at any for any vehicle. Okay, another thing which you can calculate from the graph, so these are things you can just simply measure from the graph, the queue length and the delay. Another thing which you can calculate from the graph is the total delay. Total delay is the difference between the area of these two lines. Okay, or the area between these two lines, simply the area between these two lines, simply. Okay, so how do we measure the area? We break this into two right angle triangles. You break this into two right angle triangles. So you know, for every right angle triangle, the area is half base into height. Okay, half base into height. Okay, so which you can see over here, half. Okay, base. What is my base? The time, right? The base is time. So from the first right angle triangle is from 0 till this. What is this? Time 20. Okay, the equation changes at time 20, right? So I know it is time 20. Okay, so time 20. So from 0 to 20, so the base is 20. Okay, and height is the difference of these two lines. So you can come here and measure the difference between these two lines, the height. Okay, in this case it is 80. Okay, so 160 is the total from here, from the x-axis. Okay, my height is the difference between them. Remember, I am taking the area between them. Okay, not the total area between them. So that's why 80. Okay, for the next right angle triangle, what is my time starting from 20 till 60? So the time is 40. You can see over here 40. Okay, and the difference of height same. I cannot take the difference of height here, it will be 0. Okay, it will be 0. So that's why here. Okay, if you have a line, let me see if I can. Not this. If you have line going like this and then this, okay, so it is changing the slope here as well. It changes the slope from here to here, and then again it becomes, so you will take then 3 triangles, right angle triangles, one from 0 till 20, another one from 0, or from 20 till this point, and then from this point till the end. Okay, so we'll take 3 right angle triangles then. Okay, now for this triangle which is in the middle, you will take the mean of the heights, because the heights in the first triangle it was easy, right? Here it is 0, here it is difference between them. Okay, for the last triangle again, here there's a difference, and on the last point it becomes 0. So the difference you can only get it from one point. But if you have a right angle triangle in which at both ends you have a difference in height, you will take the mean. Okay, so it will become like a what do you call, trapezoid, I believe, no, parallelogram, something like this. Okay, I forgot the name, but it becomes like this. Okay, so the number of right angle triangles will depend upon at how many points the difference in height can be taken. Okay, how many points the slope is changing. Okay, so in this case, in the case of this question, the slope is only changing at one point. Okay, so we made 2 right angle triangles. If it changes at more points, you will make more triangles. Okay, so this is what you have to keep in mind. So this graph can give you Q length, it can give you the time, the delay time for any vehicle, and it can also give you the total delay. Okay, any questions? Is it clear? Okay, moving on. Like I said, we will be doing examples. Okay, so this is now the second case, time varying demand and constant service rate. So demand is varying according to time and the service rate is constant. Okay, just to give you an idea what I mean by varying demand by time, you can see the equation over here. Okay, so if t is in minutes, every minute the demand is changing. Every minute the demand is changing. So this is what we mean by time varying demand. So if you compare this to the previous case, full first 20 minutes, no change. Next many hours, no change. Okay, so this is the type of demand, change in demand we are looking for when we say time varying demand. Okay, so this is what we mean here. Okay, just give me 1 second. So you can read the question over here in the meanwhile. Okay, so we again have a park example. I don't know, they love parks. What can we do? Okay, the entrance to the park opens at 5:45 and the booth starts at 6. So people actually start arriving before the park opens, like they can get in the queue. I don't know what type of park, maybe Disney World or something. Okay, only kids are mad enough to go even before the park opens. But anyways, people are going there before the park opens. They get in the line 15 minutes before the park opens, and they have a deterministic rate of service which is 20 vehicles per minute. Okay, and 20% of the vehicles have priority passes. Okay, so they have a separate booth. Okay, they have a separate booth. So now we were talking about one channel, right? One channel. So for every type of vehicle there is one channel, so there's still one. Remember I gave you the example of intersection, right? So on intersection, if you have, for example, only one lane for straight, so there are three lanes, but for one movement there's only one lane, so we'll still consider it as one channel. We'll still consider it as one channel. Okay, so same thing happens here as well. You have, yes, we have two gates, but each gate is for a specific type of a person. Okay, so I cannot consider it two channels because both of them are not available for all the people. Okay, so if you have two gates and both of them are for the same type of people, then you will consider it as two channels. Here still one channel. Okay, so 20% of the people have special pass and they go from a different gate. So whatever arrival you have, 20% of that will be from one gate and the remaining 80% will be from another gate. Okay, and the first gate which is handling 80%, okay, the normal one, okay, it takes the service rate of that gate is 20 per minute, and the special gate, it takes 15 per minute. Service rate of the special gate is 15 per minute. Maybe they are giving them kava or something, okay, while serving them, because they are special people, right? Special gate. So they are taking like more time, they are serving less people. Okay, and the demand is changing according to time as per this equation where ts time, and t is time and it starts after 5:45. So t is measured from 5:45. Okay, so we have to find out the average delay per vehicle for the non-priority pass vehicles and the priority pass vehicles. I will show you in the next slide how to do it for the non-priority pass vehicles, and you can take it as a practice example, do it for the priority pass vehicles. Okay, so I will do it for the normal gate. Okay, for the normal gate, and you can do the same thing for the other gate. Okay, so the other gate will be having 20% vehicles. Okay, this is the only difference there. Okay, so we have a number of equations and derivations, so pay attention now. Okay, first of all, the demand, number of vehicles arriving with respect to time, is given by this much. Okay, where t starts from 5:45 am. Okay, so if you take so this gives you the arrival rate. Okay, if you take the integral of this equation, it becomes a number of vehicles. Okay, so this is the equation for arrival rate. Okay, rate of arrival, not the number of vehicles arriving. Okay, so this whole thing per minute, the vehicles are arriving 17.2 minus 0.2 into something per minute. Now I want how many vehicles. Okay, how many vehicles in time t, the same thing which we did in the first example. So to get that, I will do the integral of this equation. Okay, integral. So because I want to multiply with the time, right? I want to multiply with the time. Okay, so I will take the integral because you are multiplying. If you were dividing, I will take the derivative. Okay, but now I want to multiply, so I will take the integral. Okay, so when the rate is given, you want the number, you will take the integral. Simple rule. Okay, so this was the equation. When you will take the integral, it will be this thing. Okay, so it was 17.2. You will multiply with t, and this will be zero point 0.2 into t square upon 2, right? Upon 2 because of the square. Okay, when you take the integral of 0.2 t, it will be 0.2 t square upon 2, where 2 will be because of the integral. So 0.2 upon 2 will be 0.1. Okay, so this was 17.2 minus 0.2 into t square divided by 2. Okay, so it became 17.2 minus 0.2, sorry, 0.1 t square. Okay, so this is how we got it. Okay, so this is it. Okay, and we are doing it from time 0 to time t. Okay, so this is the integral. Now what are we doing here? This is what? Now I'm doing it for the non-priority gate. Non-priority gate will have 80% of the vehicles. Okay, so I have to subtract the remaining 20% from it. Okay, so this 20% is subtracted because they will go to the priority gate. Okay, the special gate. So this is what is done here. Okay, so this is the integral, the full integral, and minus the people who will go from the other gate. Okay, so you open the bracket. So this is what, so this 0.2 is not because of this 0.2. Okay, this 0.2 is the 20% which is going from the other gate. Okay, so you open the bracket and you subtract the times which have similar t's, t and t square, and you get this equation. So this equation gives you number of vehicles arrived during time t. Okay, number of vehicles arrived during time t, not the rate. Okay, so this one was the rate, this one is the number. Okay, so this one was per minute, this is number of vehicles. Okay, then vehicles arriving and departure. Now for q, for as you can see what we did here, the delay is calculated when the q becomes 0. Okay, when the q becomes 0, arrival is equal to departure, right? Number of vehicles arrive equals to number of vehicles departure. So that means no q. So I need to find a time when both of them are equal. I need to find the time when the q becomes 0. I will calculate the delay up to that time. Okay, the delay will be calculated to that time. So they told me on the non-priority gate, remember, non-priority gate, the vehicles are serviced at 20 per minute. Okay, 20 per minute. Okay, but this so 20 into t. Okay, but this t when they start serving, so serving starts at 6 o'clock. Serving starts at 6 o'clock. Okay, but my t, the t I'm using in the equations, is measured from 5:45. Okay, so in the first 15 minutes we are not serving anything. So the t starts when the time crosses 15 minutes. Okay, so between 5:45 till 6 there is no serving. I'm measuring t, I'm putting t in the equation, which is from 5:45. Okay, so in the first 15 minutes there is no serving. After the first 15 minutes it starts serving at 20 per minute. When you will do it for the priority pass, it will be 15 per minute. Okay, so this is what you see here. Okay, this is the gap between the t of my equation and the time of serving of the gate. Okay, so 5:45 to 6. So this is number of vehicles arrived, number of vehicles departed, 20 per minute multiplied by the time. Okay, so you made them equal and you get the time when the q becomes 0. The q becomes 0 at 33.6 minutes. Okay, initially 5:45 the q will start, no serving, 6 o'clock, q has been established, and then when they start serving, the q will start to go less and less, and in approximately half an hour it will completely go. Okay, I will go quickly through it now. So I already have the equation for number of vehicles arrived. Okay, so I'll take this time and put into this equation. Okay, so how many vehicles arrived in 33.6 minutes? 372 vehicles. Okay, now I want the delay. Okay, delay is the difference of areas between number of vehicles arrived and number of vehicles departed. Difference of areas between integral of this equation and integral of this equation. Okay, whenever you need the area under the curve, you take integral. Whenever you need area under the curve, you take integral. Okay, so integral of this equation minus integral of this equation. Okay, same thing which we did here for this graph, but here it was lines. Now we have curves, so we have to go the mathematical way. Okay, so this is the integral of the number of vehicles arrived equation. This is the integral of number of vehicles departed equation. Okay, and in both of them you will put the time 33.6, because we know when the delay is when the time is when the queue is finished. Okay, when the arrival becomes equal to departure, so 33.6 minutes. Okay, so after you take the integral, you will put the time 33.6 everywhere. Okay, and what else? Yeah, and they have 372.102, which is what? I will have a look, but the thing was you can take the integral. You will take the integral and you will put the time 33.6 seconds. Okay, I don't know why 372 is there. Okay, maybe they already took the integral and they inserted the values. Okay, but the point is integral of this minus integral of this at time 33.6 seconds, 33.6 minutes. Okay, so you will get the total total delay. If you want average delay, total divided by number of vehicles. Average delay, total divided by number of vehicles. Okay, so you will get 8.86 minutes per vehicle. Okay, which is total delay divided by number of vehicles. Okay, number of vehicles came from here. Do you have any questions in the method? I will check what this is the last equation. You have any question with the method? Okay, now for the attendance, I will just ask you to raise your hands, all of you can do it together.